Okay, time to go over the examples. Example 1 with taking derivatives of logarithms. Using the chain rule, you want to see that this is a baby function inside of natural log of blah. The derivative of natural log of blah is 1 over blah. The formula is 1 over x, but I'm saying blah so that I realize I've got a baby function, and so that I properly use the chain rule and give mommy her baby and multiply by the derivative of that baby with respect to x. And the derivative of x cubed is 3x squared. You'll notice that the textbook talks about the log rule with chain rule. You don't need to memorize another rule unless you want to. You don't need to memorize that if it's natural log of u, that you're getting 1 over u times u prime. You just need to understand how to use the chain rule, and you don't have to memorize a whole nother formula. Example 2. I have another baby function, sine x, inside of the natural log of blah. The derivative of natural log of blah is 1 over blah. And then I give mommy her baby, and I multiply by the derivative of sine, which is cosine. And if I simplify, I will notice I have cosine divided by sine, which happens to be cotangent. Example 3. This time the natural log of x is the baby function. Anytime you can circle a function inside of another one, that makes it a baby. Now I have the square root of blah, or blah to the 1/2 power. Taking the derivative, I get 1/2 blah to the negative 1/2 power. Chain rule says, give mommy her baby, and then multiply by the derivative of that baby, and that's 1 over x. And then let's simplify that a little bit. Looks like everything's in the denominator. We have a 2 and an x in the denominator, and a square root of natural log x sitting in the denominator. Example 4. Now the base is not e. You've got to make sure you memorize this formula. Notice the baby. So you have log base 10 of blah. When you take the derivative of log base 10 of blah, the formula is 1 over a constant times blah. That constant is always the natural log of the base. Make sure all of this is in the denominator. So again, the derivative of log base 10 of blah is 1 over natural log 10 times blah. Now, give mommy her baby and multiply by the derivative of the baby, which I can just throw in the numerator. Derivative of 2 by itself is 0, and then derivative of sine is cosine. Example 5. I have a big giant baby in my logarithm. But there's something special you can do with logarithms that you cannot do with any other type of function. If I did this derivative as is, I would have to start with the chain rule for using logarithm. Then I'd have to move to the quotient rule for the inside of it. And while I take the derivative of the bottom, I'm going to have to chain rule it. Wouldn't I like my life to be easier? Yes, I would, if I could. And I can with logarithms. You can expand your logarithm using log rules. If you don't know your log rules properly, don't do this. You'll mess up, and you'd rather do more work and have a correct answer. So the rules for logarithm, if you have division inside of one logarithm, that's the same as subtraction between the two logarithms, where the numerator logarithm leads. And I can avoid a chain rule in that second one by realizing I have a 1/2 power inside of a logarithm, and I can bring that constant multiple of 1/2 outside the logarithm to multiply. So logarithms can tame product, quotient, and chain rule, but make sure you know what you are doing. All right, now this is the best I'm going to get for an expansion. From here, I'm going to take the derivative. So dy dx is equal to, for natural log of blah, the derivative is 1 over blah. Give mommy her baby, multiply by the derivative of that baby, which is 1. And then minus constant multiple times, and then I take the derivative of natural log of blah, which is 1 over blah. Give mommy her baby, multiply by the derivative of that baby, and that's how quickly you can do it if you condense. And from there, it's a matter of simplifying. So at this point, you can get common denominators. So I multiply this fraction by 2 times x minus 2 on the top and the bottom. I multiply this fraction by x plus 1 on the top and the bottom. Then the denominators that are in common will be the denominators for all. And I have 2 times parentheses x minus 2 minus parentheses x plus 1. And I'm going to quickly go, that is 2x minus 4 when I use distributive property, minus x minus 1. And now I can finish this up. Two x minus x gives me x, negative 4 minus 1 gives me minus 5, and voila. I have one more example. It'll be quick. I just want to present to you, if you do have those absolute values and a logarithm, when you take the derivative, you can basically just ignore them. The only bonus that maybe you don't recognize, or maybe you do, is that you have more domain going on for this problem than if you did not have the absolute value. So when I take the derivative, again, I'm going to ignore the absolute value and just look at the baby function inside of that absolute value, because we found out that the derivative of the natural log of absolute x is 1 over x, plain and simple. It just has a domain of all real numbers except for 0. So that means I take this baby, 2 minus 3x, and call it a blah. And I'm now taking the derivative of natural log of blah. Derivative is 1 over blah. Give mommy her baby, and multiply by the derivative of that baby. Derivative of that baby is negative 3. And literally, we have just ignored the absolute values, which causes this derivative to have more domain than if it didn't have the absolute values. As far as the equation that you see for the function, neglecting domain, you get the same thing either way, with or without the absolute value. All right, so that is the logarithms and some examples. Now I'm going to move over to examples with the linear particle motion, and I'm going to talk you through example 1. It's a very long example and it covers everything. I've got the answers here ready to save us a little bit of time. So you are to A, find the velocity at time t. You should know that that means you're taking the derivative of position, and that derivative is 3t squared minus 12t plus 9. There's your velocity. And here's the textbook writing it out. Now, I've got ready to go all of these questions. There are a lot of them. Perhaps you want to take a nice little screenshot of that. And now we keep going. Next is, what is the velocity after 2 seconds and 4 seconds? Since I've already found the velocity function to be 3t squared minus 12t plus 9, the only thing I'm doing is I'm plugging 2 into t, a little arithmetic, plugging 4 into t, and a little arithmetic. So I end up getting these two answers, provided that I can add. Ha 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 ha. That's always sometimes amusing. Moving on to C, when is the particle at rest? That's the question, when is velocity equal to 0? So we take that velocity equation we found, and it's a quadratic, so if I'm trying to solve for what makes it equal to 0, I want to factor it. And I can see that I get time 1 second and time 3 seconds for when the particle is at rest. Make sure when you solve particle motion problems that you know the domain you are working with. What is the time domain you're working within? Because it's possible that these answers may not be within the domain. This problem did not give domain. Some of them do. It just said, here's a function. Now, moving on to part D. When is the particle moving forward or moving in the positive direction? And if you recall, that is when velocity is positive. So you're going to take what you already did with factoring velocity, and when you solve the inequality, some of you have forgotten how to solve inequalities when you're dealing with polynomials. I get it, so I'm going to talk through it. What you want to realize is this quadratic is equal to 0 at 1 and 3. So if I look at this as a number line for t values, these are the t values where the velocity is equal to 0. This creates 3 sections of time at which the velocity is forced to either stay positive for that entire time or negative for that entire time. You very importantly need to look at this as a dynamic, well, for these two, a dynamic duo. If they are both positive or both negative, velocity is positive. As far as the t minus 1 times t minus 3, I'm not going to concern myself with multiplication by positive 3 if I only care about positive negative. So if I plug in, for example, x equals 0, which happens to be in the interval of negative infinity to 1. If I plug in 0, I get a negative number times another negative number, which gives me a positive number. I don't need to know it's positive 3. I just need to know it's positive. Then for this interval, I can pick a number in between there. Again, I don't actually have to calculate the velocity at that time. I just need to know, is it positive or negative? So if I plug a 2 in right here, I'm going to get positive. If I plug a 2 in here, I'm going to get negative. Positive times negative is negative. Boom. Then I can pick some x coordinate within the interval of greater than 3 and plug that into t, and I will say it again, I only care about whether I'm getting positive or negative, not the actual number. So plugging a 4 in here, I'm getting positive. Plugging a 4 in here, I'm also getting positive, and a positive times a positive is a positive. So the answers are, it is moving forward when t is less than 1 and when t is greater than 3. You can write that in interval notation if you like. I'm going to keep going. For drawing the diagram, you have to see what they mean by that. What they're doing is they're taking, they're saying here that it's moving horizontally back and forth. And they are letting you know that my location at time 0 is position 0, and that location is here. At time 1, my position is 4, and so this is where you have a value of 4. This is representative of S. That means that I'm not looking at plotting values of T, I'm plotting the values of S. So this is S equals 0. This is S equals 4. And after analyzing a lot about this problem, and actually you almost need to do this diagram after you do some later problems, because you need to look at when does it change direction. It may change direction when velocity is equal to 0. So what was that velocity equation? My velocity equation in factored form is 3 times t minus 1 multiplied by t minus 3. And actually, I got a little bit of that up here. And I saw that I will go through a direction change at time 1, and I will change direction at time 3. And you can see that they're showing moving in the positive direction from time 0 to time 1. But you have to plug those numbers into the original S of t function, which was that third degree polynomial. And that's going to give you the number 4. When I plug 3 into my position function, the third degree polynomial, I will get 0 for my S value. So what that is telling me is during the first second, I move forward from position 0 to position 4. Then, as I go from time 1 to time 3, it moves in the negative direction backward and comes back to position 0 at time 3. After time 3, it simply moves in the positive direction. But if I just sat here and drew it like I just did, you would not be able to read the diagram. So what they're doing is they are allowing time to move this diagram upward. But it's only moving it upward at times where it goes through a directional change. So you're just going to draw like, hey, I'm moving to the red, I'm moving to the right. And then when you switch direction, in order for us to see that, you have to allow time to go, stretch it out. And then I'm moving to the left, I'm moving to the left, and then let time stretch it out. So you can see these separate movements. That's what they mean when they say draw a diagram. All right. Now, total distance traveled during the first 5 seconds. Oh, goody, total distance traveled. That means you need to know when is velocity 0, which we found. Velocity is 0 at time 1 and at time 3, and I'm looking at the first 5 seconds. So if you like, you can say time and then position, which is S of t, but they are using the function f to represent f. S of t, whatever. It's the third degree polynomial. So during the first 5 seconds mean I start at time 0 and I finish at time 5. I need to know the position at those 2 times and the position at time 1 when my velocity is first 0 and time 3 when my velocity is 0 again. So we have actually found these values already. My position is 0 at time 0. My position is 4 at time 1. At time 3, my position is 0, but I have not found my position at time 5. So, oh goody, I get to go back to that third degree polynomial and plug that number in. So I'm going to head back over there. All right. And I'm going to plug 5 into all of those t values. I'm going to speed up the process by letting the answer to the textbook tell me that value. Oh, look, it told me it's 20. So once you have all of the values or all of the positions at the beginning and end time of your time frame and every time the velocity is 0, then it's a lovely process of how far did I travel from 0 seconds to 1 second, and make sure you absolute value it if needed. And then from time 1 to time 3, while I traveled in the negative direction, I went how far? And then from time 3 to time 5, how far did I travel? Subtract the positions and you get how far you traveled. And then you add them up and voila, 28 is the total distance traveled. Now, part G wants the acceleration at time t and after 4 seconds. So you're going to be better off if you take the velocity function not factored. So 3t squared minus 12t plus 9. 3t squared minus 12t, and then was it minus 9? Forgot already. It was plus 9. So this is velocity. I need to get acceleration by taking the derivative. That means I have 6t minus 12. So that gives me the acceleration at time t. And then if I want to know the acceleration at time 4, all I do is I plug 4 into the t, and out pops 12 meters per second per second. Part H, let a calculator do it. Just let a calculator do it. I am fine if you use a calculator on graphing the position, velocity, and acceleration functions. You should know how to graph all of them. But yeah, moving on. Speeding up versus slowing down. That is very important. That means you need to look at when the velocity is 0 and when the acceleration is 0. So we already found, and I already did a number line looking at velocity and the fact that it is 0 at time 1 and time 3, where this is representing the time axis. And then I am putting positive or negative for whether the velocity is positive or negative over those time intervals, which we found just a tiny bit ago. Now, acceleration has not been found yet. With acceleration, I want to look at the equation that I got, 6t minus 12, and I want to figure out what makes it equal to 0. So I factor a 6, I get t minus 2. That means the acceleration is 0 at time 2. And I need to know, is acceleration positive or negative on each of those half number lines? So if I plug in a number like 0 into t, I'm going to get a negative number for acceleration. If I plug in a number like, say, positive 3, I'm going to get a positive number for acceleration. Now I'm going to bring those two together and make sure that I put down the negative and then positive. Now, what you have to do is look at the two together. Write down on this number line anywhere that either velocity or acceleration is equal to 0. And then take a look. What I'm going to do is I'm going to write V and A. And velocity is positive before 1, negative between 1 and 3, positive after 3. Acceleration is negative before I hit 2, positive after I hit 2. And now I am speeding up when the signs are the same. I am slowing down when the signs of velocity and acceleration are opposite signed. And then I am able to get the answers for speeding up and slowing down. And and you can see it all in here. I probably should write it down. There's another lovely graph, blah, blah, blah. You can look at it if you like. But let me just say real quick, I am speeding up. In other words, my speed is increasing over the interval from 1 to 2 and 3 on. Now, I am not going to worry about the endpoint issues as to whether I include them or not, because there are issues in math about the endpoints and increasing and decreasing. And I'm going to talk about that later. If you are doing an application problem, and this is an application problem, you should bring logic in. And it does not make sense to be it does not make sense to be increasing and decreasing at the same moment in time. I'm going to say that and just say that there's a controversy in math about the definitions of increasing and decreasing. And I'm on the side of they should not include endpoints because it does not make any sense in application problems. But anyway, speeding up, that's your answer. And then speed decreasing or slowing down is going to be negative infinity to 1, 2 to 3. All right, that's it. That's all you need to know. Have fun, and I'll see you online.